Hello there, people. Just waiting for a few more people to arrive. I see Ryan's joined us. Didn't manage to catch us in lesson today, did you, Ryan? No. But we're glad you're here. So today's plan, we've got approximately 2 hours. Whether you stay here for 2 hours or not, it doesn't really matter. What we're going to do is we are going to go through as much content as we can. So far we have completed component 1 in its entirety in our A-level studies, and we've started now component 2. So we're going to cover everything we're going to need up to component 2, and that should prepare us pretty well for our mock exam, which is next week. If there is anything or any questions, please do stick them in the chat, and I will do my absolute best to get to those questions as I go through. Also, if there's burning topics that you really want to cover, then you just let me know. I'll do my best to cover them. So, here we are. So we've got all of this interesting stuff to cover everything from component 1. And what I'll do is, for everyone, I will send this out at the end, of this presentation. So here we are. Now you can see on here, there's 9 different subject areas that we need to cover. The first one being data structures, which is quite a nice topic, and you covered that in September. So let's jump straight in and look at arrays, records, stacks, queues, trees, linked lists, and even hash tables. So the only thing there that doesn't seem to appear that often is hash tables. And if we get stuck straight into this is from the specification, so we need to be able to describe, interpret, manipulate data structures, including arrays up to 3 dimensions, records, stacks, queues, trees, linked lists, and hash tables, and be able to describe the manipulation specifically of records and arrays. So with data structures, we've got 2 categories. We've got static and we've got dynamic data structures. So on our dynamic data structures, dynamic means they can expand and contract, whereas static means that it is set at the beginning of the program and it cannot be changed. So whether you've got static data structures, they are quite limited because you must rely on what data has been provided. Hello Max, welcome. Now, static data structures, they're easy to program because you know exactly how much space they'll take up, and you know how many elements you have, for example, whereas dynamic is usually better because we're going to keep adding in information to those. So they will expand, but they are more complex to implement and to keep track of, keep on top of, and to search, etc. So with arrays, quite straightforward. Arrays are the most simple of all data structures. They contain, an array has 3 things. It has an identifier, which is the name. It has the elements, and it has an index. All indexes in data structures are 0 based. And we can access them using the index of the array. When we get to 2-dimensional arrays, normally the exam hits 2-dimensional arrays, and that's because it's slightly more complex, but you're dealing now with rows and columns instead. So if I was to picture a 2-dimensional array, I'm looking at having my single rows and my columns. Whereas in a single dimensional array, you just have one single row and everything has its own index here. So your index goes on the top and your index goes on the side. I forgot what numbers are. we go. So here, this code shows that we have 2 dimensions. So this is us declaring 2-dimensional array in pseudocode. And you can see there, you can use rounded brackets or square brackets. We won't penalize you for that. And you can see the outer brackets there. And inside each one, you've got a second set of brackets there. So we've got Sam, Lucy, James, Jack, and Jane. Then we've got, on the next one, we've got Peter, Sarah, Adam, Karen, Verity, and then we've got Emily, Edward, Dominic, and Justin. Good evening, Mahadi. Look at that. Welcome. Blast from the past. So if you printed names 1, 2, you would print out Edward. Columns, rows. Now, 3-dimensional arrays are much more difficult to visualize. So the key bit to this, if I show you, you've got basically 1-dimensional array is a single row, 2-dimensional arrays is rows and columns, 3-dimensional arrays is basically groups of rows and columns. So before, this would have just been a 2-dimensional array, and this would have been a 2-dimensional array. Together, when you group those under one identifier, then you've got a 3-dimensional array. And I'll be honest with you, I don't tend to use these. I normally use 2-dimensional arrays when I'm programming because it's just easier for me to do that. So a single row in each table can be represented by a 1D array. Then the entire table can be represented with a 2D array. Then you have 2 classes worth of data. That will then be a 3D array. Now records, we've just been studying records inside files. So a record is a set of data items that are all related to a single entity. Inside a record, you've got a collection of related fields. And unlike an array, a record may contain data items of more than one data type. So for example, this is my record data structure. Each one of these is called a field. And you can see here that they've got different data types. And you can hijack an array, force it to have more than one element. So you can have an array of records. Yes, an array of records, I said. And inside each one of these, you would have your record with your multiple data type fields in there. This would be another record with your multiple data type fields in there. This would be another record. Okay? And you go on and so forth. And that's how you basically get around the problem of having single data types in an array. Now, the next thing to talk about is a stack. Stacks are very, very useful data structures indeed, and they are a last in, first out data structure. So adding to a stack is called pushing, taking off from a stack is called popping, and then stacks are usually, they're implemented using an array or a linked list to hold the actual data. And most data structures do have a pop, a peek, and a push function. And all we can do is basically pop off the top, push onto the top, or peek at the top. And that's why it's last in, first out. So the last thing put on top will be the first thing out. And that's ironic, isn't it? Because it is actually Pancake Day. Who'd have thought that? Now, a couple of things that you might get asked to deal with when you're talking about stacks is to create in pseudocode a pop or a push feature. Key points to get around here is your pointer top and you've got your value. So if this was 0, this is 1, 2, 3, 4, and 5. You can see here this array has Sam. Sam's at position 3. The pointer top is position 3, so you have to record where the top of the stack is. Oh, it's going to do this all night. It's very, very, very annoying. Then, to beat at level 3. I'm sure the students can answer that for you. So with your pointer top, you have a value which says my stack pointer top. So you basically say my stack at position 3. my stack at position 3 is set to empty. So this gets removed and it says empty. And then pointer top equals pointer top minus 1, which reduces the pointer to Peter. And then you return the value, Peter. Sorry, you return the value of Sam, sorry. Okay. If you want to push data on, you have two parameters. You have the data you want to push on and the pointer top itself. So the position pointer top, once we've deleted it, is now 2. So this is the pointer top. And the data itself here is, it looks like it's Alex later on. So we push it on. So in order to push it on, we don't want to put it in Peter's position, so we have to increment the pointer first. That's why we do this stage here. Increment the pointer first, and then put the data in that position where it says empty. So you might get asked to pseudocode a pop and a push function. The next data structure to look at is a queue. And we love queuing. So a queue is a first in, first out data structure. Think of queues like the ones you find at supermarket checkouts, with the first person being in the queue will be the first person to leave it. Now, you can also pop and push on a queue as well. So if you think about this here, Sam, Peter, Emily, Edward, empty and empty. Pointer front is position 0. So this is the front of the queue at position 0 here. Then it says value equals my queue pointer front. So what is at my queue at position 0? And that value would be then Sam. So Sam goes in there. My queue pointer front gets the position of empty. So this gets removed and empty goes in there. And then pointer front equals pointer front minus 1. In actual fact, there should be a +1 because we increment up to Peter being our pointer front. When you push, data goes on and the pointer of the back of the queue is provided. So my queue pointer back, so down here, is given the value of data. So again, that would be Alex. So Alex would be put in place of empty. And the pointer back is incremented, so we know where the back of the pointer is at all times. So again, in an exam, you might get asked to write a pop or a push function for your queue data structure. Okay, sorry about that, I was just clearing my nose. Got a bit of a cold today. So next thing to look at is the tree data structure. And you know what I'm going to say. A tree, a binary tree, looks the same as a binary search tree. You have nodes of your tree and each node has a maximum of 2 branches coming off it. And that is a perfectly balanced binary tree. Perfectly balanced. That is fantastic for searching because it's equal on either side, which is really good. Now, if it's unbalanced, it can take a lot longer to search, etc. And you don't want to give one side more processing time than the other side. So balanced is good. So a binary search tree looks exactly the same, but we can apply 3 traversal methods to our tree. So the data on the left branch of the node must be less than the data in the node, and on the right hand side the data must be greater than data held in the node. So Lucy is less than Poppy, James is greater than Poppy. Now you'll see exam questions like this, and I'm sure you've done lots and lots and lots of exam questions. Okay, now the trick to these kinds of questions is you're going to be asked to draw the binary tree. So what you have to do is you have to take the first value as the root node. Okay, now you've taken the first root node, and then what you have to do is you have to compare Samsung to it. So if you think about it, when I tell students A, B, C, D, E, F, G. Now I tell them to write out the alphabet because it helps them out. You can quickly see there that Samsung is after P, so you'd have to point down here and you put Samsung down there. The only time I see students having problems with this is if the students get the same letter. What is that, TV? Never even heard of that. That is ridiculous. Toshiba and Techwood there, that will be put in your exam to try and trip you up to see how you deal with doing this. So what you have to think about is, right, if I've got two of the same, then I'll compare the first letter. They're the same. Go and compare the second letter then. So in this case, E, Techwood, is earlier than O of Toshiba. So this here would go left of Toshiba in this case. So if I went to, so put black punt in there, I then go to, so it's black punt there. So the next one is Toshiba. So start Phillips again. Toshiba's after it, so I'll go to the right. Toshiba is T is after Samsung, so I'll put Toshiba there. Then you come along again, Techwood, so that's after P, it's after S, and then the O, T-O, Toshiba, so it'll go to the left of Toshiba. And that's all you got to do. Keep placing them, checking each node as you go through, making sure it's in the right place. Oh, Mafos has joined us. Good to see you, Mafos. Hope you're doing well. Then it says, part B, add hindsense to the tree. So you just follow the same process. You say, is H before or after P? And in our case, it's before it. Is it after B? Yes. So you go to the right-hand side of that. And that's worth 4 marks. Okay, and that's what the completed tree actually looks like. Then for part B, once you've had hindsense in, that's where it goes for the 4th mark. Hopefully that's not too difficult for you. Apologies, I am moving pretty quick because we do have a lot to get through today. Now what you might get asked is you might get asked to use pointers and arrays to actually control trees. So unlike stacks and queues, there is a range of different ways to traverse a binary tree data structure, and each method will return a different set of results. So you have 3 traversal methods, the first one being pre-order. Now my advice to you here is to take this extremely slowly. Students often, all the students that I've come across often know the traversal order. And that will be node first, followed by the left, followed by the right. Node, left, right. So what I do is when I perform this, I will say node, left, right, node, left, right, node, left, right, node, left, right, node, left, right. And the reason why I draw this on here is because it helps me keep track of exactly what I've done. Okay? So what we're going to do is start the root node, traverse the left subtree, then traverse the right subtree. That's what it means. Node first, left subtree, right subtree. So you take, if it says N for node, you write that down. So here, I'm going to write down D. So then I scribble this out to say I've completed the node part. Now I can only tick this off if I complete the whole left subtree. So I go down to the next one because I've not completed the whole subtree. I go to the left and then I've got node again. So I'll scribble that out and I write down the node. Then I've got to complete, in order to scrub that off, I've got to complete the whole left subtree of B, which is all of this. Oh, I've got a node again, so I write that down. A goes in there. Then I search the left subtree, there's nothing there. Scrub that off. I search the right subtree, there's nothing there. Scrub that off. That's it. Fully completed the left subtree. I can now scrub this off. Traverse the right subtree. Go down. So I've got node of C, search the left subtree, there's nothing there, right subtree, nothing there. I can scrub them two off. Now I've completed the right hand subtree. After that, because I've done all the left subtree now of D, I can scrub that off, and I've got the right subtree to tackle now. So I go to the node, scrub that off. That's F. I go left. I've got a node here, scribble that off there. I've got the left subtree, nothing there. Right subtree, nothing there. I get rid of it. Done the whole left tree now. The only thing I've got to do is the right subtree. I've got a node on G. That's left subtree, right subtree, nothing there, nothing there. Get rid of those. I've done the right subtree now. I've done the entire subtree, and that is my traversal done. Now, as an examiner, what I look for is the first mark you'll get for the root node being in the right place. If it's a pre-order traversal, pre means first, okay? Node first. So I should see the root node, which is this node here. That should be the first element in your list. Even if you get all of this wrong, as long as your root node is in the right place, you're going to get a mark for it. So remember, pre-order, node first. The next one, in order traversal, you've got left, node, right. So everything gets left, node, right, left, node, right, left, node, right. So first, you've got to go left, you've got to go left, you've got to go left. I look at the left subtree, nothing there, I've done that. Then I can take the node. So I need A first, so I've got the node, I go right, nothing there. Up here, I've done the left subtree now. Next, I take the node of B, and I go to the right subtree, and I go left, nothing there. I go node, I write that down, and I go to the right, nothing there. I've done all the right subtree now. I go back up to D, and the left side is complete. What I do next is I write down the node. Done that. Now I've got the right subtree to contend with. Right subtree sends me down here. Follow the left rule again. So I look at E's left subtree. I've got the node next. So there's E. I do the right subtree of E, and there's nothing there. Report back to F. I've done the left subtree now, F. Take the node. That's F. Complete the right subtree, which is G. Because I've looked left, I've looked at the node itself, and I've looked right. Done the right subtree now, done the right subtree now. I've got everything I need there. And look where the node is this time. It's in the middle. In the middle. So again, 1 mark for the node being in the right place. 2 marks for the correct traversal. Finally, a post order. Post means at the end. So this node here should be the last thing I'm writing down. So you've got left, right, node. These are all on my YouTube channel. You can check these out. Like and subscribe, people. Like and subscribe. That's a shameless plug. How many subscribers am I away now? Who knows? So we go left, root node. We go left at the root node. We go left at the root node. We go left at the root node. Root node. Nothing there. Nothing on the right hand side. Left side, right side. Then we write the node down. It's the last thing we write down. A live sub counter. Maybe. B. I've done the left side of you now, B, so cut me some slack. Oh, I wish that would... That's the worst design ever. That thing that keeps popping up with this pen. That thing there. So annoying. Done the right subtree. Got to go down to the right subtree now. So a B, we go to the right subtree. We've got the left of C. Nothing there. Tick that off. Go to the right. Nothing there. Tick it off. Then finally we take the node of C. So I've done that. Got those two. Go back up. Done the right subtree now, B. Take the node of B finally. So I've done the left subtree for D. Now it says do the right subtree first before I can tick it off. So I go down, I go left, nothing there. I go right, nothing there. And then I take the node of E. Write it down. Back up, left side's done now. Okay, do the right side. Go to the right hand side, I go left, I go right, I go node. So I take the node of G, back up to F. I've taken that now, F. Okay, take the node, and then take the final root node. Again, the last thing, that should be 1 mark, and then the other mark for the rest of the set. So these are the kinds of questions you get. Carry out a pre-order traversal. So you can pause that and have a look. There you go, pause it and have a look if you wish. There you go, carry out a pre-order traversal. There's the answers to the traversals if you want to pause and have a go. Okay. So just like stacks and queues, it's possible to implement a binary tree using an array or a linked list. It's more useful to use a linked list, as this allows to implement a dynamic binary tree. So using linked lists, the nodes of a tree are made up of a piece of data as well as the pointers to the addresses. So you would have seen a linked list before, I hope. What's going on? We're going to get to it in a second. Here, you have 2 parts to each node of a linked list. You have the pointer and the data. Pointer and data. So a binary tree gets constructed. So the first item becomes the root node. Items earlier or in the same position go on the left and on the right. So you get questions like these. And feel free to have a go with these questions. Again, you can pause the video. I'm not going to stop and have a go with these, but by all means, have a go. You should have done most of these in class anyway. These are the answers to those questions. Now, the only thing that I see is when it says questions like this tend to trip students up. You've been told to draw this tree, so you draw the tree. No problem with that. 2 marks. Show how the above tree or below tree could be represented using a 2-dimensional array. You read 2-dimensional array and you start to panic. Don't do that. 2-dimensional array is just a table. Whenever you read 2-dimensional array, just think table. Table, table, table. Left pointer, right pointer, data. Yeah? Root node, left, right. That's it. That's what the table's representing, right? Then, each row is the index position. Always start at 0. So here, Newport is my root node at position 0, 0. Newport's left pointer points to position 1, which is Canterbury. Look, Canterbury, position 1. Oswestry, 2. Warrington. And you'll say to me, John, how do we make sure that it's the right number? How do we? Why is that 4? Why is Bath 5? Why is Derby 6? I'll tell you something. It doesn't matter. Absolutely not a problem. As long as you've got the correct pointers to the data, nobody cares what order it's in. Normally, it's alphabetical, but it doesn't matter. As long as your references are correct, you'll still get the marks. Now, if it doesn't have a pointer like this rugby, right? It'll have a -1 in there. Okay? Okay. Had to clear my nose again. It's getting too bad. Right. So that's the only bit where I can see students getting stumped on questions like that. That one's fine. Okay, removing nodes from trees. Another question you could get. So if we remove... Oh, I've lost my cursor. If we remove a node, basically, if it's just a child and doesn't have anything coming off it, it's just fine. We'll just get rid of it. So that's fine because it has no children. Whereas this, for example, has a child, you will then point to it directly, right? Now, if you have two children, like if I was deleting F, for example, which one would go first? Okay. Now, what normally happens is the one with the highest priority goes first, so the one that comes earlier in the alphabet comes first. So it's normally the left one. All right. So that one would be E followed by a G after that. So bear that in mind. Linked lists. I like linked lists. They're quite nice because they're easy to get right in the exam. But linked lists are good because they're dynamic all the time. They can grow. They are very, very useful. And I like to think of a choo-choo train because each carriage of the train is basically your data, and it has a pointer which connects between the carriages of a train. So here you've got Sam, Peter, Emily and Edward. Each one has node and a pointer. And linked lists are made up of nodes. They're used to implement almost every other data structure that we know about, almost. But you must have data and a pointer. Without that, you have nothing. So to add a new node, when you see something like this, node star, okay, that means a pointer. So the node class pointer has a new node, and you create a new node. Capital like that means it's a class. And if you remember stuff from object-oriented programming, a class is a template or a blueprint for something. So new node is given the value of new node from the class, which means you inherit all of the procedures or methods, should I say. So for example, new node calls the select data and passes Dan. Sorry, set data and passes Dan. So Dan is then attached or added into the structure itself. So Edward has no pointer going from it, and that connects to Dan, and Dan becomes the tail. Oh, sorry, the head of the linked list. Now, if you're drawing this, I saw this in one of the exams that we did earlier on, before December, I think it was, a bit earlier maybe. Oh no, it's January. You can easily insert a new node if you know where you want it to be put. Just make sure that in your exam, if you do this, connect, make sure you use arrowheads to connect the data, and show clearly that you have destroyed the pointer. If this was in your system, you would connect to Julie, connect to Peter, and then destroy the pointer. If you destroyed the pointer first, Peter and Sam would be lost forever. Because in computer science, in memory, we have something called garbage collection. It disappears. Off it goes. So, works the same way for deletion. And the final one before we move on to the next topic is hash tables. Hash tables are very good because they have very fast retrieval of data. It uses direct access, so we can just use a hash function, get the information, index and return it, and do whatever we want with it. So no matter the amount of data that's stored, it can find the data really quickly. So they store data in what we call an associative array. So that's key pair values. Then we use a hashing algorithm to generate the index. So if you remember what we've just done in class, we've looked at direct and random access. We use hashing functions and we use data to generate an index that is numeric. So here we are, hash table on the right hand side. So our index has 0, 1, 2, 3 and 4. So to find someone like Lou, using a linear search would take a very long time if the array was very large, because we go one by one in a linear search, whereas if we know the index, we can find the position in the array almost immediately using direct access, because we can just jump to position 3 and find that Lou is there. But we need a way of working out where Lou lives in the array. So to do that, we use the hashing algorithm inside. We have data. Data goes into a hash. Hash tells us the location in the hash table. So a table where the actual data is stored on the right hand side there in pink, and a mapping function called a hash function or a hash algorithm that you create. You create it. So what problems can we have in the future? Well, two items in the same location, because your hashing algorithm's garbage, will create a collision. Collisions created by hashing functions can lead to more records being stored in the single block, which means in the block you have to linear search the block. And there's two options when you store information in blocks. You have to create an overflow and place the record in there, or create a new file that contains more blocks and rehash every record to that new file. That should be very recent in your mind, because we've just done that. We've just done it in our file handling topic. And if you say you don't know it, I don't know. You're a terrible person. Overflow. So when we overflow, we can use the back end of the file. So if the location is occupied in the block, we use the next available location. And if the end of the file is reached, we wrap around and start searching from the beginning again. So flags, we can use flag overflow, where we flag the original block and we move data into designated overflow areas for linear searching. So if the block's full, we have to put it somewhere else, and that is the overflow. But we need to tell the system and say, hey, listen, there's a flag here. So the overflow's being used, you better go and find it in there. Now that's bad. We don't want to linear search the overflow, because that goes against the point of this direct access in the first place. Okay? So some questions there, if you want to have a go and pause. There's the answers for you. Look at question 12b II. Bit of pseudocode. Traversals. Let's look at some logic operations. Okay? Something that a student didn't know today that I thought was quite interesting was logical operations. Okay? If you were asked in pseudocode to tell me where or what the logical operation was, hopefully you would think of things like and, or, not, NAND, XOR, NOR. They tend to be the typical ones that we look at, but we have to look at Boolean Algebra. Now, if you don't know these, you are going to struggle. That's because this relies on super logic, super logic. Now you can't see there, this is just a typical way that electronics people write their Boolean algebra forms here. Realistically, all of these would have a little full stop in between them. Now I'm going to leave that on there, but you need to be able to do things like this where you go, what is 1 and A? So truth tables, people, you need to be able to do truth tables. This condition, A, can only be a 0 and it can only be a 1. They're the only two options that A can be. It's Boolean algebra. Here, this side is 1. So if I said to you in the AND gate, what is 1 and 0, it's going to be 0. Because anytime you AND something with 0, you always get 0. This one will be 1 and 1, which will give you 1. Now what does this look the same as? It looks the same as this. Therefore, it's the same as A. This one's the same. Anything ANDed with 0 will always be 0. Anything, A, anything ANDed with itself will always be itself. Anything ANDed with a not will always return 0 because you're flipping it. You're flipping it. So you have to get used and comfortable to doing these, especially like these top ones. Oh my goodness, that was terrible. Can I back that off? Oh my goodness. That was the worst line I've ever drawn in my life. Let me get rid of it. Look at the skill. So there you go. Get rid. Right. Those are basics, right? These ones you have to apply in your algebra. Things like commutative law, you can swap terms around providing they've got the same operator. Associative law, very useful. Not that common though, but very useful. Distributive law, it's just like distributing brackets, GCSE algebra. Absorption is factorizing. Okay, factorizing them, breaking them down. De Morgan's law is A2. So guess what, people? Guess what? It's almost 100% likely that's coming up. If they're going to ask you Boolean Algebra, they're probably going to ask that because Boolean Algebra is the only difference on the A2 spec when you look at these laws. Okay? So get used to it and get comfortable. Right. Take a question. I won't spend forever on this. Take a question like this. A or C and A and D, or A and not D, or A and C, or C. Some people go, John, what you on about? Now what you have to do is you have to think, what do we do first? Where do we even start? Just start hacking away at it? Like some psychopath? What I would do is say, why is that not? Okay. This D here and that D there are not the same thing. Because that's not D and that's D. They're not the same thing, right? Now what I would do is I would factorize this. Now basically we're going backwards before we're going forwards here. What the hell? That's not simplification, is it? So if you think about it, if I said A and D or not D, right, in brackets like that, if I multiplied that out with that, you've got A and D, haven't you? And I multiplied that out with that, you put an or in between, you've got A and not D, right? Look familiar? Yes, because it's the same thing. At this point now, what is D, or not D? Well, D can be 1. So if D is 1, not D, is 0, isn't it? If D is 0, what does that make that? 1. In an OR gate, as long as you've got a 1 on either side, you will always return 1. Always. That's why we get that. Okay? Then, if you AND A with 1, it will, if you edit a condition ANDed with 1 will always return itself, because A could be 0, which means that it would overall return 0, and A can be 1, which means that overall it will return 1. So it's itself. So that cancels down again to just A. And then we have to look at, okay, now we've got that in place. I've used the commutative law. Swap these round so it looks a bit nicer. You don't have to do that, but it's nice for the examiner. Okay, make the examiner happy. At the end of the day, they're giving you the marks, aren't they? Then we can use something called the absorption law or the redundance law. Break that down again. Because we just applied that on that end, we can do the same thing again and break it down again. That would be A or C. I've got loads of these, but I don't want to spend forever doing them. What about this one? Feel free to pause it and have a go with a little whiteboard or a piece of paper at home. From my experience, people either get this or they just do not get this. So if you don't get this and it's horrible and you're scary, take your time. Have a go at it, keep cracking away, keep trying to apply your laws, etc. You might get it wrong a few times, okay, but try and work towards the correct answer. So for this one, I would use the distributive law to distribute the brackets, okay? If you can't do anything else, always distribute the brackets because you will get a mark for doing it. Then the second set of conditions, which is these ones, I would expand these ones. And then you guessed it, the third set of conditions, I would expand those ones as well. Gives us lots of things to play with. After that, you can see here, I like to funnel. When I mark these questions, I funnel them like this. Funnel, funnel, down to 1 there. So I can see exactly what you've done. Exactly what you've done. Try to keep these conditions all in the same line so it's easy to see how you broke it down. A and C, or A and C. If you've got a cat and a dog, or you've got a cat and a dog, guess what? You've got a cat and a dog. Okay? So that breaks down. Funnel that again for marking. Funnel, funnel, funnel. And then, like before, we used our redundance law. So let's have a look at this on a different page. We're just going to go over to a different page so you can see it. Continuing on. A or A and C breaks down to just A. Then at this stage, we've got A or A and B, which breaks down to just A. Then we've got C or C and B, which is the same as what we did up here before. Just A swapped out for C. So we can use the redundance law or the absorption law again. We've got A or C again. Okay, you can use these videos for the OCR exam board. There is similarities involved. I do know that they use this Boolean Algebra, so that's all good. They also use the formal terms as well. But I'll skip through these. Feel free to pause them. And have a go. It literally just takes practice and patience, this, people. You will get it, I promise you. Took me ages to learn. So many questions. Okay. So. Oh, that's a good point, Max. Thank you very much. Stone 997. Right. This bit. Well, if you start now, you never know. You might learn it all by then. Who knows? We want to be able to apply logical conditions to logical operations to conditions in programming, such as clearing, masking, and encryption. Right? Your job is to remember the logical operation that performs clearing, masking, and encryption. Have a little table somewhere, right? You can choose either one of these. It doesn't matter which one. And or XOR. They both do the same thing, but you've got to be careful. Now, masking is when you're trying to show 1, 2, 3, 5, 6, 7 bits of a register, right? So if the question said, I want you to show me the third most significant bit, most significant, least significant bit. They will always point to the one or ones that it wants you to show after the masking has been applied. So the masking process can perform this task by applying the AND logical operation with the mask. So if I take this information here, the original data, I apply my mask looking for the third 1 bit. Then I AND them together. 1 and 0, 0. 1 and 0 is 0. 0, 0, 0. 1 and 0 is 0. 1 and 0 is 0. 1 and 1 is 1. 0, 0 is 0. 1, 0 is 0. Now you ask me, I get this question every time. They say to me, yeah, but John, what if you had 0, 0, 0, 0, 1, 1, 1, 1, and it wanted you to show what this bit was here? How would you do that if it's 0? What are you talking about, you idiot? You just put, look, there's a mask done. What if I wanted to show this one and this one? We just changed the bit for a 1. Does it show the state of those bits? Does it show you what that bit was? Yes, it does. Does it show you what that bit was? Yes, it does. So, breathe, people, breathe. It's fine. So, masking. What about clearing the register? Clearing means to get rid of all the information out of there. So, you can do it one of 2 ways. You can take the original data. You can and the original data with all zeros, and you'll get your cleared register. You must write this down somewhere. That is a mark in itself. All right? You must. And finally, clearing registers with an XOR. Okay? XOR gate. I don't know if you've come across this before. All right, but an XOR, basically, if we've got two of the same values, it will return 0. If the values are odd, like 1 and 0, that will return 1. If it's 0 and 1, that will return 1. But a 0, 0 will return 0, and a 1 and a 1 will return 0. Okay? So 0, 0, 0, 0, 0, 0, 1 and 1, 0, 1 and 1, 0, 0, 0, 0. Everything's 0 because the mask is identical to the original data, which means you will run this rule and you will run this rule, making it always, always, always 0. And finally, this is another A2 topic here, people. Encryption. Encryption. So, the job here, right, is to take ciphertext, right? Go back. The original data, right? This data here is plain text. I need to turn it into ciphertext that you can't understand or read. You need to have a key. You make this up. This is your key. Make it up, whatever you want, whatever numbers, zeros and ones, make them up. Use the XOR gate and XOR them together. So 0 and 1, 1, 1 and 0, 1, 0, 0, 0, 1, 1. Now the beauty of this is symmetric encryption, so that means you can reverse it by applying the same thing. This was the ciphertext from the previous slide, so the text that you can't read anymore. You take your original key that you created and you XOR it again, and it should return back to the original data. Original data. Okay. Any questions so far? No questions? Fine. Suit yourself. Oh, look at that. We're at like 54 minutes. What have we been doing? Oh my goodness. Oh my goodness. Let's skip past those questions. Oh, dearie me. Oh, questions. Right. Oh man, this is the biggest topic in the world. Oh man. Is there anything anyone wants specifically from that list wants me to cover? If I do it all, I'll be here all night. What have we got? Take a look. Whack it in the chat if you want it. I'm just going to plough through and see how far I get. Right? So an algorithm is a set of mechanical or sequential steps that are used to take an input and return an output. Right? How do you represent algorithms? You could say, right, if you can't remember how complex and technical that sounds, you can just say it's basically the steps that we take in order to fix or process or create something at the end and return an output. Right? It's a set of steps, like a method to baking a cake. Right? How do we represent algorithms? We've got pseudocode, flowcharts, and structured English. Okay, that's how we represent them. Now, in addition to that, we've got flowcharts. Flowcharts, they have strange symbols. The symbols are normally very strict and straightforward. This exam board seems to have its own little mind about flowcharts, okay? But start and end, decisions, so like this, for example, Input boxes normally use a parallelogram for inputs instead of that weird looking shape. Okay, outputs, end. So you could look at that. They're very intuitive, they're easy to read because diagrams are simple and straightforward. You can represent algorithms using pseudocode as well. Now pseudocode, if you can't pseudocode, or you struggle to pseudocode or get your point across with pseudocode, then just use code, right? Because if you get the point across what you're trying to do for the examiner, they might give you some marks for it. So there is a list of pseudocode from this exam board. Everything from global variables to casting to outputting, etc. And it's very, very Python-esque, etc. But if you said something like begin, set the sum to 0, so set the sum variable to 0 for I equals 1 to 10. So I is a local variable, starting at 1, going to 10, input some value from the user, sum equals sum plus value, end for output sum. Very simple, very straightforward. Pseudocode is a skill, you got to practice it, so use algorithms to do that. There's loads of them out there. If you want some, let me know. I'll get loads for you, thousands of them. Recursion. Now, recursion is a function that calls itself within itself until a base case or a terminating condition is met. All right, it provides a succinct way to carry out the same operation a number of times. So I've used this in class before. You've seen it, but we think about a factorial, for example. If you don't know what it is, give it a quick Google, have a look. But here's a piece of code for it. Now, the easiest way to spot recursion inside an algorithm is to look for the name, yes, the name of it, inside. So this is the name of the function, and look, it's inside itself. Now, when does it end? When a base case or terminating condition is met. So only when the n of this algorithm is 1 will you stop and return 1. Otherwise, you're going to call another copy of the program again and pass it n-1 this time. Pass it another copy, n-1. Another copy, n-1. Another copy, another copy, another copy, another copy, another copy, another copy, etc., etc. Okay? Recursion. It's very good and very efficient when it wants to be. However, every time you open up another copy of the program, you put it on the return stack and it creates the same amount of variables get created again. So your memory is being abused at this point. Looking at validation and verification, they're used to ensure any input provided is as correct as it can be. It cleans the data before it enters your system. Two terms you need to be aware of. Validation, which occurs before data is committed to storage, and verification is when it's committed after. So a couple of key validation checks. You've got character or type check, a length check, format check, existence or a presence check, and a check digit, which is specific for barcodes. So it's a mathematical operation where you add the numbers up of a barcode and the end number should be a 1 or a 0. Validation checks. You've got double entry and human proofreading. Yep, they'll read it. You've also got screen verification, like captcha codes, for example, or giving them the chance to visually check and correct any errors in there. And now we look at key programming terminology, variables and constants. So a variable is a name space in memory that can contain a single piece of data. The data type of a variable, such as an integer, a real, float, boolean, character or string, it determines what the data inside the variable contains. A constant doesn't change throughout the life of the program. Now, the good thing about constants is that if you change the constant's value in one place, it will change everywhere in your program. And normally it's things that don't change very often, like pi or VAT. Scope, two types, local and global scope. For you, you'll probably get asked on an algorithm where it is. So you'll be asked to tell us what line number is local, what line number is global, that kind of stuff. A local variable only exists until the subroutine, which is forgot everything then. A subroutine is a function or a procedure. So it'll only exist while the subroutine in which the variable is created is still alive. If you close that procedure or function down, it will die and it will release its memory. A global variable exists throughout the program execution and can be read or written from any subroutine. Now, parameters, I like what's that? Calc VAT, right? You can pass in amount, right? So parameters normally are inside brackets or parentheses, and parameters can be passed in two ways. So you've got by reference and by value. Uh-oh. Come on. Oh, the team's joined us. Now, if we pass by value, that means a copy of the value is passed from one subroutine to the other. And if the value is changed by the subroutine, then the original value remains unchanged. The key word in there is a copy. Whereas if you pass by reference, the actual variable from one subroutine to another gets changed because you're passing. Why is it being weird? What? Strange. It was being weird then for a second. So if you pass by reference, you pass the actual variable. So really, when I say actual variable, I'm talking about the memory address. Okay? Because you're passing it the original memory address, you can then go to where it's stored in RAM and change the value. We don't normally pass by reference because it leads to errors. That's what it leads to. So we normally don't do that. We pass a copy because then it can't get changed and we only use it. Now, I'm going to show you some algorithms that you can practice your pseudocode on. It's being weird again, it's being weird again. Why did it do that? So weird. Some algorithms here that you can practice pseudocoding on. Let's go through this. Time is tight, people. Time is tight. Right. Now, it's going to be difficult. I'm not going to go through the sorting algorithms because I've got videos on each one of these, okay? But this is what you need to know for your sorting algorithms. One, you need to know what they are and how they work. So you need to be able to describe and explain what the algorithm does for the sort. Also, you need to be able to dry run them. Yes, so you'll be given the information, you'll be given the pseudocode, then what you have to do is you have to dry run and put data through them. Then, after that, you also have to know how to pseudocode them as well. Pseudocode. Now that could be from scratch, people, so you really do have to be careful because it's not an easy task at all to do that. Also, the final part. So this is what I'll be doing next year. Well, if you make it to next year, that is. Got to work hard for your exams. So you also need to be able to list the best and worst case here. So be very careful with that. So the best case is normally what's the best running case and what's the worst running case involved in there. So we've got our bubble sorts, insertion sorts, we've got our quick sort as well, and the pseudocode. Then we've got our searches, so our linear search, a binary search, and we've also got Dijkstra's algorithm. Okay, now Dijkstra's algorithm is a little bit different because this is a shortest path algorithm, so it uses a network of nodes, and what it does is it will assign the initial cost of each node the infinity, and then the starting node is set to 0. All other vertices are put in a list of unvisited nodes, and you set the start node to be the current node, and as you visit each one, you can never go back to the node again. So for example, okay, Dijkstra's algorithm, quick little go of this. So what we do is say, right, we're at node A, so we're currently here, and we're trying to get to Z. Now you have to check every node. So for example, you can get to B, from A to B, it's going to cost you 4. Okay, so 4 is going to, so you can get from A, cost of 0 via nothing. We're already at A. So to get to B, it's going to cost you 4, and you're going to go via the A node. No problem. Okay. Now, this one, from A, you can also get to C, but you can't get to F, you can't get to E, and you can't get to D, because the only thing that A can see is B and C. So A gets to C for a cost of 3. And what does it go via? It goes via A. Now, once that's done, A has been completed. So I'm going to scribble that out because we've finished, done. Then, our rule is we move to the next lowest cost node. So that's 3. In this case, that's the lowest cost out of these two. So now I'm here at C. C can look at E, it can look at D, but it cannot go back to A. So C can get to E for a cost of 10, but you have to take the current cost on top of that as well. All right? So I can get to E for a cost of 10, plus the cost of getting to C in the first place, which means it's going to cost 13. And I went via C to get there. After that, C can get to D for a cost of 7, plus the cost of getting to C in the first place. That means it's a cost of 10. And I went via C. C can't do anything else now, so C has been completed. I scrub that off. Next lowest cost. I've got 4, 10, or 13. Next lowest cost is B. So I'm going to place myself at B, and I'm going to see what I can look at from there. I can look at F. I can look at E. So B to F is going to cost me 5. But what did it cost me to get to B in the first place? 4. So 5 plus 4 is 9, and I went via B. B can get to E for a cost of 12, plus the cost of 4 to get there in the first place. So 12 plus 4 is 16. So E, is 16 less than that? No, so we leave that as it is. We've visited all the nodes from B now. Where next? 10, 13, or 9. I have to look at this one. I'm at F now. F can get to Z only for a cost of 16 plus the 9. What's that? 24, 25? 999. Woo. Where was that? 19, yeah, 25. Okay, so Z for 25. Now, I went via F for that. So, done, can't go anywhere else. What's my next lowest cost? D for a cost of 10. So, I jump to D. What can I get to? I can get for E for a cost of 2, plus the cost that I already took to get to D, that's 12. So, I can actually get to E for a cheaper cost via D this time. And that's it. Can't go anywhere else. Scrub it off. E, the final one. E is 12. To get to Z for a cost of 5. 5, 6, 7, 17 is cheaper than 25. 17 via E. Okay. Now, done that. How do I work out the fastest way of getting there? Well. You have to start at Z, so you put Z down. And how did you get there? I went via the E node. There's E. E is here. I got there via D. D via C. C via A. A, C, D, E, Z. So the fastest path was A, C, D, E, and Z. That's the fastest cost for a total cost of 17. And that's Dijkstra's algorithm for you. Okay. Moving on. As our worked example. So that's a nice little summary for you to summarize all of our sorts and searches. You can freeze frame on that. Take a quick screenshot. Then look at big O notation. Ho, big O notation. So big O notation is basically just a way of classifying algorithms based on when you add more data in, how is it going to work? Sorry, blow my nose. If you wonder what that weird sound was. 1K subs. Oh, look at that. Easy, minor work. Do I get my play button? Does it come in the post? Tell me how it works. Thank you very much. Thank you very much. People, you're all here to witness it live. Live at 1914. On the 21st of February 2023, John made it. I can't see how many subs I've got, so I hope you're not lying to me. Max, you dare? I will reduce the value of your coursework. I don't have that power, but I wish I could. So big O notation. Look at me. I'm staying humble. Staying humble. You can get a signature next lesson, yeah? Friday. So big O notation. I don't have a camera set up at the moment, but that would be good, wouldn't it? Would be good. Yeah, I'll bring the heated C in. That's an inside joke, that. Inside joke. So let's have a look at our different summaries of our big O notations, our classifications. So we've got order of n squared, order of n log n, order of n, order of log n, order of 1. Face keyboard. You know what? I'm going to get so much RGB. I'm going to it's going to be just colours, mass colours, microphones, big headsets, mechanical keyboards, everything I hate in the world. I'm going to get it. I'm going to get it sorted out. Again, nice little summary for you. The lengths that I go to prepare for you students. Little summaries like this are fantastic for learning. Wonderful. But order of n squared basically means that the addition of an element has a disproportionate impact on the time and space required. So additional elements, as you add them in, it doesn't perform very well. I've gone back down to, oh, look at that. 1,000. Wow. Order of n log n is a quick sort, so it's a recursive algorithm. Linear search is order of n, so the time taken is proportionate. It's in direct proportion to how many elements you've got to actually run through. Order of log n means that additional elements don't cause a great increase in time, so they're pretty good algorithms to use, especially with the data set sizes that we have. Order of 1 is constant time. So remember what I said in class? Constant time, you need to be specific when you're giving algorithm examples to say it is a bubble sort or an insertion sort for its spatial complexity, not its time complexity. Time is different. I don't plan on retiring yet, Matib. So these are the kind of questions you get. Now they always come in groups, they don't just come standalone. So big O notation is a method of describing the order of efficiency of an algorithm. Identify the order of efficiency of the algorithm illustrated in the example above. It's constant time. Time to complete and size of data. Don't forget, if you're asked to draw a graph, you need to label it. So constant time. Draw a graph of an algorithm with an order of n. Order of n is direct proportion. It's a linear graph. Looks like that. Describe an example of an algorithm with an order of efficiency of order of n squared. N squared looping through a list. That would be, as the size of the list increases, the time taken increases in direct proportion. Nested statements, increase in time is directly proportional to the increase in the input size. And the last one is a logarithmic relationship because it has diminishing returns. Examples include a binary chop, which is basically a binary search. We're looking for a logarithmic relationship. You'll get examples like this in your exam with code. And I taught you how to basically manipulate these and cheat a little bit to spot things faster by looking for nested selection statements. But again, I've got a really good video on how to work through these kinds of questions. Now, when it comes to programming constructs, you've got sequence, selection, and iteration or repetition. Sequence means code goes in order. Selection means if statements or select case statements, which is basically an if statement, based on conditions. So you can have if, else if, else if, else if, else if, else, for example. Repetition, for, whiles, do's, do until, repeat until loops. Any kind of repetition of code is called repetition or iteration. Something that you're probably not used to is a count variable and a rogue value. A count variable is basically when we do for I equals 0 to whatever, and you say next I. So next I would be a count variable because it counts the index, it increments by 1 every time. Or a count could be, I don't know, the number of full buses that pass through the bus stop, right? It's a variable that you increment every time. That's a count variable. Last one, a rogue value is basically a terminating condition. Now, a terminating condition could be something like the value can't go below 0, or it's not allowed to be equal to 15, whatever. That is a rogue value. And the three main programming constructs that we look at is sequence, selection, and iteration. You need to be able to spot these in code. So what types of constructs can you see in here? Any idea? Sequence, selection, or iteration? What have you got? Four. Look at that, people have gone shy. Keyboard warriors over here. Now, you've got this one. This example is showing sequence because the code will run from start to finish. So it'll start on line 2, work its way down to 5. Then it'll go on to private sub here when the form loads, and it'll run these 4 lines of code in order. So it's sequence. Next one. What constructs do you see? What do we see? I don't think it was delayed. So we've got in there, we've got sequence because we've got if statement, sorry, we've got selection, sorry, because we've got if statements there. And we've even got a logical operator as well, look at that. Ooh, fancy, 2 conditions on there. Constructs. We've got sequence. So we've got selection. We've got a little bit of sequence in there. Selection with the if statements. If statements all the way down. Have we got any loops anywhere? No. And there we've got our loop. So a for loop there, nice and simple. Indentation. What? We do have indentation, but that is not a construct that we're looking for. Okay. Oh. And you can have someone, let's see if someone can tell me what this is. Any idea what this is? Constructs have we got specifically this? What's this? Try and be as specific as possible. Excellent, Max, well done. It is nested. Nested just means one inside another, so you can have nested for, nested selection, etc. Oh, come muck it. Yeah, it's well done you. Look at that, big O. It is order of n squared because there's 2 loops in there. Well done you. Look at that. You know what? Maybe he does listen. Who knew? Anyway, so here, this is the kind of question you would get. The 2 sections of code below carry out the same task. One section of code uses iteration and the other uses recursion. How the hell do we know it's recursion? Because the name of the function is inside itself. This one just uses iteration. There we are. Now then. So describe iteration and describe recursion. Give 2 advantages of using an iterative function compared with a recursive function to solve a given problem. That is quite a nice question. Lots of marks on offer. This is the kind of stuff that you're looking for. Iteration is repeating a set of instructions, whereas recursion is a method where the function calls itself within itself until the base case is reached. Finally, iterative solutions tend to be easier to program, easy to understand and maintain, and functions that just iterate make no demands on the stack space, so there's no extra memory needed where it might be needed in the first place. Each time a recursive function is called, certain values are placed onto the stack, and it takes time and uses memory. You have to keep the ordering when it's placed on a stack, and it can cause your computer to get the blue screen of death because RAM will get filled up. That's the problem. Okay. Now, let's see where we're at. Which one do we want to do? Time is running out, people. You've got 1.4, 1.5, 1.6, 1.7, 1.8, 1.9. Or data representation questions, so a bit of binary stuff. What do you want to do? We have to get selective now, people. No, Max. No max. Unless, I mean, people have to start donating. You know what I mean? My time is precious. My hourly rate, you can't afford it, unfortunately. .9 on the exam. Legal? Ooh. Well, have you covered it, Matib? I can't possibly say, but have you covered it in class? That's right, it's Rack. And 1.8, 1.8. I'll wait for a few more to come in. 1.8, 1.9. Interesting. You know what I'll do? Off to the side here, I'll just check your mock exam, Matib, where you can't see it. Ooh, interesting. Some good questions though, Matib. Uh, 1.8, so 1.8, 1.5. We haven't covered it. Yeah, but AS you did, didn't you? Didn't you? Oh yeah, okay. Ooh. Tell you what, you've done most of this today. Oh yeah, this is pretty good. I'm pretty happy we've covered quite a lot of this, to be fair, today. Okay, I can confirm. No AS content. No. Everything from 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8 can be covered on the mock exam. 1.9 is not covered. 1.9 is not covered. So there you go. That's a gift for that from me to you. You're welcome. But there is some binary stuff in there as well. But I did tell you that earlier on. I did tell you that earlier, that before half term. That's it. Just for the live stream, folks. Everyone else, if they're not here, you're missing out. You know what I'm saying? That's how we roll. Anyone else? Right, so 5.1.5. Right, so let's jump into 1.8, 1.9. Right, let's do 1.5, 1.8, and 1.9. See where we get up to. System analysis. Whoa, that was software engineering. What the hell? I'll tell you what, this presentation has been crafted over the years. It's amazing. Let's just use this. Right. Boop, 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 boop. Look at this. Right, system analysis. Approaches, waterfall and agile methodologies. There are loads more out there. They're quite old now, so they don't really get used that much, although some of them do, but they've been adapted. So for things like rapid application development, Scrum methodologies, there's loads out there that you can use. So feasibility, investigation analysis, changeover, testing, maintenance, backup and recovery, documentation. They're from the specification, people. Feasibility, can we do it or not? Investigation methods, you've done them for your coursework. Questionnaires, document collection, interviews. What's the fourth one? Can't remember. What is it? Observations. There you go. Right. So you've also got changeover methods. Methods of changeover, pilot, direct, all that sort of stuff. Testing, white box, black box testing, alpha, beta. Maintenance, adaptive, corrective, perfective, and backup and recovery. So let's have a look at some of them. So the waterfall approach has a sequential design, one after another, in which various developers draft up all the requirements up front. It gets agreed. Everyone knows exactly what's needed. The teams get decided, and then you go. Everything has a milestone, and it happens bit by bit. So you deliver the milestone and then you give it to the end user. That's it. Move on to the next one. There's no going back. It's very, very rigid, a waterfall methodology, and that's its main disadvantage. It's very rigid, but it has very, very, very good documentation. Everything is documented. That's why developers don't like it, because you have to document everything. I've asked you to annotate your code, and that's hard enough. Not many people have. I know who you are, and you're on the live stream. Okay, if the client's needs change, the project goes on, and the project will take longer than predicted, and that can go over budget and over time. The agile approach is an incremental approach to development in which the developers start off with a simple project design instead of a huge document. It focuses more here on the developer themselves. It allows them a bit of freedom, a bit of flexibility to do what they need to do to get the job done. So it can be difficult to predict when the project will be completed, how much it'll ultimately cost. Things can run on, things can take longer or shorter, who knows? So changes can be made after the initial planning phase. You have little increments where you can go back, take feedback on board, test, go again, tweak, etc. But what you don't want is the end user giving you more things to do by saying, oh, can we just change that? Or can we just put this in? Or can we just do that, etc.? Because that is called project creep, when the project starts to drift away from its original objectives because you're asking for feedback all the time. You have little sprints, a couple of weeks long normally. Get your sprint done, hand it in, do documentation, carry on. So normally, in the exam, you can focus on the advantages and disadvantages of the waterfall methodology, and also you don't be afraid to draw diagrams to show what you're trying to do, because you'll always get marks for those. A picture is worth 1,000 words after all. So to successfully answer exam questions on system lifecycle, you should be able to recommend a particular model over another based on the scenario you've been given. So that's our software development lifecycle. As we know, you've got a number of different roles in there. So you might have the stakeholder, the users, the programmers, and the project managers, and also system analysts who do the investigation and the feasibility study and all that sort of stuff. So firstly, in the problem definition phase, identify the problems, define what the new system could fix, meet up with the people, the clients, developers, end users. Start to write down what you think might be needed. So think back to your coursework. This is what you did. You come up with an idea, discussed it with people, talked about it, see if it was possible, that kind of stuff. And you must agree on the initial scope before you move on. When it comes to feasibility, you need to think, can we actually do it? Is it even possible? So you've got to think petal. Political. So if I make it politically, will it ruin my company? Will it ruin my business? Economic, will I get enough money? Time, have I got enough time to do it? Technical, have I got the people to do it? Legal, is it ethical to actually do it in the first place? Then you carry out an investigation. Observations, questionnaires, document collecting, interviews. Write down your actual requirements, your essential and your desirable objectives requirements. Interface requirements, so what should it look like? Functional, how does it work? Performance, how should it perform? You don't want a game that lags all the time. You want it to calculate in, a second. Then what we've got requirement specification gets made, gets agreed, and we carry on. So you've got observations. Really good, make people feel threatened. That's not good, but they make people feel threatened. They pick up parts of the system that are not obvious by the customer, and you can confirm information gathered through different fact-finding methods. Sorry about that. I'm slowly dying. So confirm that the information is gathered through different fact-finding methods. There's no guarantee as well that you might see stuff. So depending on what time you go and observe the business, there's no guarantee that you'll see everything in the first place. You might do a questionnaire, gets given out to loads of people, but you don't always get them all back. They're hard to create and design and to get right and to basically ask all the questions that you need. You can take documents from the people. Documents are great because you can't lie on documents unless they are redacted. So government organisations, military, they redact or basically get a black marker and scrub out lots of private confidential information. So, documents are reliable, but they can also be sensitive and restricted. Okay, it might give a limited view of the system and how it's created. It might just show you the outputs, but it doesn't tell you how the process works. Interviews. You may have been in interviews before. Lots of pressure on an interview. They are time consuming. The good thing is you can ask lots of follow-up questions as well. That is a good thing. So interviews might not be fully truthful because everybody lies. Their responses might need to be verified, etc. Then we talk about requirements. So you've got your interface requirements, which is what the user should see. Functional requirements, so key features the software will have. And you've got performance requirements. So scalability is how big it can grow, expand or contract, what platform it's going to be used on, how many people can access it, database requests, number of that kind of thing. Then you can build your requirement specification. So IEEE is a standard that we use, the 830/1998 version. That has introduction, overall description, and specific requirements. That's just a good standard that everybody follows in the industry, really. Moving on from there, you've got your design. So we might have inputs, outputs, processes. We've got data structure diagrams. We've got abstraction decomposition of the problem. We represent our designs using lots of different diagrams. Well, this is detailed, isn't it? I'll send this out if people want it. So when you abstract something, you're basically thinking how simple you can make it for the user, yet it's still complex behind the scenes. That's all to improve user experience. When you decompose things, the problem, you break it down. Okay? Decomposition, you break it down. So you've got program, broken down to interface, validation, test results, data storage, etc. The more broken down and modularized your system is, the easier it is to basically manage within your team. You design everything that you need to, like your JSP diagrams that you've built. Some people have done flowcharts or pseudocode. Some people have designed entity relationship models for their databases. Data flow diagrams to show processes. And UML diagrams, nobody's done those, but they show the overview of the system, external and internal. After you've built the thing, done software development, you test it. So white box testing is done by you as the user because you need knowledge of what's being tested. You've got unit testing, which is automated tests that are really simple to run. You've got black box testing, which is given to people outside the system, and their job is to run a test script that you provide and basically put in 2 plus 2 and it should equal 4. Right? That's a black box test. You've got alpha and beta testing and end user testing. So alpha is limited functionality, beta is almost ready for release, and you normally give it out to people for free in the proviso that they test it for you. So white box and black box, that's what I just mentioned there. Explain those. Unit tests and the data we use. So when people get to their coursework testing stage, you'll be using logical pathways, normal data, extreme data, and invalid data. So you can have extreme valid, extreme invalid, etc. You want to robustly test your system with lots of different inputs to make sure that you're covered and that your system is robust and you can't break it. And I will break it. Alpha testing, beta testing. Acceptance testing is done by the end user. So that's where you give them the final system and they say, yes, this is fantastic, or no, it is awesome. Awful, should I say, not awesome. Awful. They don't pay you. Documentation, you've got internal documentation, which is what you provide, that's the code itself. Sensible variable names, good comments, good layout, etc. It should be quite intuitive for another developer to use. Technical documentation, again, is for the developer. You pass it on to them for maintenance, or they can continue developing it. It's very techy. It contains technical specifications, all the designs, all the diagrams, all the testing that you've done so far. And then finally, you've got your user documentation, so how-to guides. So how to install, uninstall, how to use the program, resolve problems, maybe a FAQ, a frequently asked questions section, that kind of stuff. So they're the 3 types of documents that we do have in our software development lifecycle. So these are the methods of changeover that we've got. The diagrams explain it better than the text, to be honest. But direct means you're straightforward swapping, very high risk. Pilot, small pilot, see how it goes, tweak it, adjust it. That's a pretty good method of changeover because bugs can be resolved without much, impact. Parallel changeover, 2 systems at the same time. Problem with that, lots of resources needed, lots of processing. Then we've got phase changeover, where we phase the old system out, bring the new system in. Hello, Umar, thank you very much. Maintenance systems, we've got maintenance, we've got perfective, adaptive, and corrective maintenance. So perfective means it's very expensive, right? Because you've got to make sure that the thing you've created is identical to what's been asked for in the specification. Adaptive maintenance basically allows you to change for legislation, for example, or requirement change that's needed by the user. Corrective maintenance exists to remove bugs that were not addressed during testing. Now, it might not even be your system that you're testing, but maintenance contracts are very, very lucrative, and we like them because they pay well. So inside maintenance documentation that you create, you might have annotated listings, so annotate your code. The algorithms, variable lists in data dictionary. You might have a class diagram and a list of subroutines as well, and entity relationship models. So you're basically mapping out the system to see what it looks like. And finally, once all that's done and sorted, you evaluate what you've done. So requirements, does it meet the functionality set out in the original requirements? So it's always good to reflect and look back. Every single requirement must be met to be a success. Requirements should be explicit, and performance of your system, it needs to match or meet the performance that was set out in the requirement spec. If it doesn't, it's not as fast, it doesn't perform as well, then there's a chance there that the person might not pay you. Evaluation, how robust, how resilient was your system? Does it crash with software? If people put random data in, does it crash, etc.? And things like safety critical systems, mission critical systems that I was explaining today with the M group, it's crucial that it's tested and it's robust. Otherwise, people's lives can be at risk. So you want a test report produced. The user tests are done if needed. And then finally, you've got to look at the cost. Are you on budget, under budget, over budget? Who's paying for it? Are the extra costs negotiated with the end user? Are they going to pay for it? Probably not. You're going to probably have an argument with them. And also, cost reports, breakdowns of costs. What costs you so much? And we know that things like games cost so much money. It's ridiculous. Finally, usability. End users must be able to use the system. You must think of the skill of the user, how intuitive it is to use the actual software. Has anyone ever trained you to use your smartphone? Probably not. And there we are. Now, there are some other approaches you can follow, such as incremental developments. So the entire system designed before being broken into subsystems or modules. Not ideal. We don't tend to do this. Modules are then programmed one after another. Each module is designed in detail, implemented and tested before being released. The only problem is you've got to tie it all together. And with incremental development, you normally create software very quickly. It's very expensive though. Feedback is given stage by stage. And you can have a better reaction to changing requirements as needed by the user. Now, because things are in modules, you can assign different people to different sections, and therefore there's better use of expert skills. and also it encourages thorough testing in your module before releasing it. And that's where things like GitHub come in, where you have forks to systems and you bring everything back in the main branch. Okay. Now we've got our last 15 minutes left. So do we want program construction compilation process? So this is the last thing that we'll cover then today, is 1.8 program construction. That's not program construction. My links are off. This is not good. Okay. Program construction, people. The last thing today before you enjoy an evening of revision. More revision, yes, more. Now then, program construction. So you've got compilers, interpreters, assemblers. You also have got the stages of compilation, and you've got translation and execution errors. So with program construction, our job of a translator is to basically convert high level into low level. High level languages, low level languages. So compilers, interpreters, and assemblers are all forms of translators. Their job is to convert code. That's it. That is all they do. So compilers convert source code written in high-level languages into low-level languages. Now, compilers produce a standalone executable file. There is no need for further compilation, and the program is compiled once but can be run many times, and that's really useful. It also makes it really easy and straightforward for distribution. And compiled code protects the intellectual property of the developer. That's useful, especially if you're developing your own software. You don't want other people stealing your software unless you produce an open source piece of software so people can use it. Now, interpreters, they handle the job very differently. It doesn't create a standalone executable file. It translates each line of code into machine code line by line. Every single time, every time you run it. Python is an interpreted language. And with that, the good thing about interpreters is it can be used on many different platforms. Many different platforms. So the interpreter takes the first line of source code, translates it and executes it before moving on to the next one. Any machine code produced while the interpreter is running is not saved. So next time you want to compile this, next time you want to interpret this, it will have to be done all over again. Lots of processing. Now, why do we use interpreters? Because of the multiple platform issue. Okay, interpreters are commonly used for a number of different languages. In order to be able to run an interpreted language, you must have installed the interpreter beforehand. That can be a bit tricky, especially in an organization like ours. We have 1,000 computers and we have to install the interpreter on everything. So when people say to me, "Oh, Visual Studio Code, it's not installed somewhere, John. Oh, it's not in a science center." Yes, because we have to ask for it to be installed. Interpreted languages can be run on any system as long as the interpreter is installed. And the good thing about that is that the source code has to be written only once and can be run on any computer with an interpreter. You can easily inspect the contents of variables as the program is running, and you can test the code much more efficiently, as well as being able to test single lines of code. So it doesn't matter if you've got Apple operating system, Unix, Linux system, even a Windows machine, doesn't matter. Absolutely not a problem, as long as it's installed. Issue, there you go. The interpreter running on a computer needs to be installed. As source code must be compiled each time or interpreted each time, programs can sometimes run slowly. You have to rely on the interpreter to actually optimize the code rather than the programmer itself. So that's why people choose different integrated development environments, IDEs. They choose different ones like Visual Studio Code, Eclipse, NetBeans, for example. because they have different levels of optimization. Developers can view the source code, which means your intellectual property is gone. Gone. Now, when we look at the distribution of this, for a compiler, a compiled program that creates one executable file, the source code is hidden. That's good. It can only be run on the CPU architecture set that it was created for. Windows, for example. To distribute an executable file is really simple. You can put it online for hosting. You can download it, put it on a USB stick. You can put it on a CD. You can even email it to someone, I suppose. Interpreters, they're shown to all the developers, and the intellectual property is at risk. It will run on any platform, provided the interpreter is installed, and systems need to be set up before the code can be run in order to distribute this. So you can distribute it easily, just you need to make sure that it is installed everywhere. So assemblers' sole job is to convert assembly language into machine code. It is extremely quick, very quick, because assembly is a very low level language directly before machine code, which is good. The problem is we don't write machine code because it's very difficult. So what we did is we created these mnemonics for machine code instruction sets. So there we go. Now these instructions here, these mnemonics like STA, LDA, ADD, HLT, they directly map one-to-one mapping, so you convert them directly into machine code. So each assembly code instruction has a one-to-one mapping, and that means there's no ambiguity, so it can't be interpreted in more than one way, which means it's very, very quick. So normally devices at home that you've got are normally written in assembly language, like your washing machine, your coffee machine, for example, whatever. Now assembly code has got that one-to-one mapping. You've got a two-phased approach. The first phase is to convert the mnemonics of assembly language into memory addresses and make sure that they can be stored in RAM. And we store them in a symbol table. So if you remember symbol tables, we've got identifier tables and reserved words tables. We've done that already in previous lessons. The second phase of assembly involves converting the mnemonics into their binary representations and combining them with binary representations of the data. So we don't write machine code because it's bad. Prone to errors, very time consuming. So when converting assembly into machine code, use an assembler, which is the translator. So a nice little diagram for you that you've seen in lessons already is you take your source code that you write, put it in a translator, which is an interpreter, make sure it's installed, and you run it on any machine. Nice and simple. Your compiler turns your code, source code, into object code, takes any libraries you've imported, links it together in the linking process, and then at that point you can continue on and go into machine code. However, if you want to convert over from, I don't know, Windows, for example, over to Unix, you're going to need intermediate code. That's like semi-compiled. Semi-compiled code, which then you can put in something called a virtual machine. Once you put it in a virtual machine, that's a translator on a different architecture set, and you can run an operating system, for example, inside another operating system. So virtual machines have been around for an awful long time, and that allows people to use different operating systems, different programs for different operating systems inside their operating system. But virtual machines are just interpreters. That's all they are, just interpreters. Now, all you need to do is say that interpreters, the virtual machines, they run intermediate code. That's the code that they run. And all that happens is it just converts the instructions into instructions that that architecture set can understand, and that's it. Now, a virtual machine is abstracted, so it looks quite simple and straightforward, but it is not the full machine. You've not got the same power that that operating system would have on its own machine, for example. Now, finally, in our last 4 minutes, we've got the stages of the compilation process. Lexical analysis, token streams, syntax analysis, syntax tree, semantic analysis in there as well, machine code generation, and the machine code, then the linking process. Here is some code. We start with the lexical analysis stage. After that, all the white space of the code is removed, and so is the unneeded punctuation and comments. Code is turned into tokens, it's tokenized, and then error messages are produced if we can't do that. So there, then boxes represent tokenized code. It's broken down into individual elements. A symbol table or a dictionary is created. So in our symbol table, we've got reserved words and identifier tables, and tokens are checked to see if they fit the grammar using things like Backus nor form, which we've seen before. Abstract syntax trees get generated, and if it doesn't fit the grammar again, we produce an error message that will always get you a mark. Now, a symbol table consists of a reserved word and an identifier table. And questions like this ask you to draw them for 5 marks. So I told my students in here that reserved word tables have 2 columns. The reserved word created by the language itself and the hex token. An identifier table is what you've created. You create good self-documenting identifiers. Oh, I clicked next by accident. Those identifiers require you to put a middle column, which is the type, followed by the hex token. So that's what that question would look like, and that's how you get all your marks for it. The hex token is unique. You create it. It doesn't matter what they are, as long as it's a hex token that is unique. So the lexical analyzer will search through the code looking for specific patterns, and this is like validation really. So we've looked at regular expressions, we had a go at some of them on the exercises. We build regular expressions with these strange looking symbols, and it makes us conform to the grammar of the language. Now we don't need this for our exam. We don't need that anymore. But semantic analysis checks that all the variables are correct, that they've been declared properly, and that memory is available for them. It makes sure that things like real values and float values are not assigned into integers, because that would truncate them. And it checks that the operation is legal. So you've got greater than or equal to, not equal to or greater than. Then we use reverse Polish notation, and that, again, similar to Backus nor form, its job is to make sure that it's unambiguous. So a variable equals a constant, or a constant equals a variable. Well, we can't change the value of a constant, so that's not allowed, but that is allowed. And that's what semantic analysis is for. So if you don't stick to the rules, then you'll get a syntax error. And a syntax error is when tokens are passed into the compiler and they don't match any of the rules. So the syntax you write is incorrect. Your IDE normally filters these out before we even get into the compilation process to save time. The syntax has to be 100% correct before we can create the abstract syntax tree, and that's what that looks like. That is a syntax tree. We then convert the nodes of the syntax tree into machine code. We allocate the registers to allocate and change those nodes into binary, and then we optimize the machine code to increase efficiency. That's done automatically. So when you click that button on your IDE, think about all the things that go on. So many things happening. You don't even know, because it's abstracted away from you and it's nice and simple. Now I know you're all terrible programmers. I'm a terrible programmer as well, because we're not as efficient as we used to be. Higher level code means that we create more sloppy code. Programmers don't even know or care that the code is inefficient. We don't care about memory anymore because we've got so much of it. So one way to speed up the program is to limit the number of jumps it has to do. You cannot code in binary, Max. You are lying to yourself. Execution errors. Final bit now. Look, I'm doing overtime. Overtime. An execution error is also called a runtime error, which occurs when the program is running. So runtime errors are errors which will cause the program or the computer to crash even if there appears to be nothing wrong with the code itself. So running out of memory will cause a runtime error, and that could cause problems and stop the whole process. It could kick you out to the screen, the user gets a weird output, not great. Okay? Now examples of execution errors are there: division by zero, reading past the end of the file, overflow in an array or a stack, for example, underflow, trying to access out of range array elements. They are all execution errors. So code works, but we do something weird. Translation errors. So such as syntax errors. A syntax error is a translation error. So this is an error during the translation process. So syntax errors are mistakes in the way the code is written. Translation can only execute a program if it is 100% syntactically correct. Common syntax errors include spelling mistakes or variables that are incorrect, or the incorrect use of punctuation. A semantic error is like illegal variables when they haven't been declared or used yet. And then finally, the last translation error is a linking error. So you know your imports aren't linked properly and you try to call them. It'll go no, doesn't work. And that is it, people. That is it for today. If people have any further questions, or even during mock week before the exam, if you've got any further questions or need to go through any of these sections, please get in touch with me, jbr@osfc.ac.uk, or come and see me if you are a student at the college. You know where I live there, in room 241 is my office. Feel free to come down and have a look. Apologies, it's so quick. 2 hours to get all that in. I need more time. Okay? Hopefully, you gain something from that. Something. Remember the methods of revision. Little and often. Lots of memory recall. Lots of sequencing. So look back. Bring stuff back in, etc. Test each other. If you've got friends in computer science, test each other. Flashcards. All that sort of stuff. Low stakes testing. These are all the methods to success. So hopefully we perform excellent in our mock exams and we can go full of confidence into the final exams. Thank you very much, people. I'm going to sign off now. Enjoy your evening. I'll see you soon.